Hi, I'm here with Peter Daly.
So I look after our on-site service and everything else, but I'm also one of our metrology team.
The Metrology Lab here at Agilent in Melbourne.
Yes.
And it's one of the few in, well, it's the only one in the
Well, no, actually
country?
there's 3 in the country that are accredited 20 hertz to 50 gigahertz.
Right.
2 out of those 3 belong to us. One's our mobile facility,
Yep.
and the other one's this facility here. The other facility that's accredited for that region is the National Measurements Laboratory.
Got it.
In New South Wales. So, yeah.
All right, let's go in. This
Cool.
is
The Standards Lab.
Woohoo, Standards Lab. Let's go, folks. And it's a balmy 21 degrees in here.
21 degrees plus or minus 1.5 degrees.
1.5 degrees, which is different from a...
General laboratory under NATA rules and under our rules is 25 degrees plus or minus, 23 degrees plus or minus 5 degrees, 5 to 80% humidity.
I'm surprised it's so wide.
For humidity?
For both temperature and humidity.
Yeah,
in a standard cal lab.
the humidity in here is an electronic environment. It's not a physical laboratory.
Right.
So it's not as critical for humidity as a physical laboratory would be.
As in physical standards,
Physical
dimensions
standards,
and
dimensions,
all that sort of stuff.
weights and measures, the hardness. They're probably more impacted by humidity than we are. We are more concerned with things being too dry than being too wet, because it gives us an ESD problem, electrostatic discharge if it's too dry. Within our laboratory, if you look at the floor, it's a particular floor. It's an ESD floor that's bonded properly and allows us to maintain what's an ESD safe environment. The average time when you pull your jumper off and you feel a zap, you're discharging about 3,000 volts worth of potential. So ESD is important to us, but our environment in our standards lab is very tight temperature-wise because of the precision required with the standards we're working with. That is particularly with the precision multimeters that we're talking about, the 3458s, and thermal voltage converters, and our resistance standards. Now they're all tied to one of 7 fundamental SI units, and they are particularly sensitive to temperature, particularly the voltage and thermal converters. That's why this, and resistance, that's why this part of our laboratory has such a tight environment. We also have some general gear in here as well. We do instrument calibrators, and our instrument calibrators are multi-vendor, what we call multi-vendor products. They're not actually an Agilent product that we're calibrating. We started calibrating them because we needed the calibration done, and we needed the calibration done in a competent manner. Having done that, we got to the stage where, okay, so we got accredited for it, and customers started asking us to do their calibrators. Right. Became a huge challenge for us. That was okay. So we're not actually supporting our product; we're supporting our customers, who in many cases are competitors, because they can't get that sort of service that they need, that accreditation, that precision from the supplier. So they come to us to it. It's escalated.
Got out of hand?
It got out of hand. We're now doing them not only for ourselves locally, we're doing it for other hubs overseas. We're doing it for our customers within Australia, our competitors within Australia, customers from Singapore, India, Malaysia, the United States are now sending us the calibrators.
I find it remarkable that they send their calibrators all the way here to Australia to be calibrated.
We're just very good at what we do.
You're just very good.
We're just very good at what we do.
They do take us seriously, folks, as you'll find out. So this is where they calibrate the calibrators.
Even with the calibrators, you think a calibrator is a low frequency device, 20 kilohertz maybe. Most labs are accredited to 20 kilohertz for oscilloscopes. All right, that's great. If you've got a 500 meg oscilloscope, how's your calibrator going to take care of it?
Exactly.
All right, so many of the calibrators have options on them for scope calibration, 600 meg or 1 gigahertz. All right, so our accreditation for RF enables us to give that precision on those scope calibration.
All the way up to daylight.
Almost to daylight. Almost to daylight. That's for that calibrator side. For the RF side, we're one of, as I said, we're one of 3 hubs in Australia that's accredited from 20 hertz to 50 gigahertz for RF power and S parameters.
And you've got 2 of them.
We've got 2 of them.
And one's portable, which we're going to take a look at.
Our portable laboratory, the other one's this laboratory
which is
here.
Great, and we'll have a look at that in another video, folks.
Yes,
so
no worries.
Should we have a look at the RF stuff?
The RF stuff, at this station here, our calibration engineers and technicians use this system. This is primarily for power sensors. Now, your average power sensor is a device like this. This is an N-type sensor, 8481. It's good for 18 gigahertz. Some people will tell you that the best way to calibrate this sensor is to hook a reference sensor up to a source and measure it, and then compare your results, which is a method of calibration. We actually have a system in place that is a NIST system, which uses 3 sensors.
NIST being the National Institutes of
Science and Technology in the United States. That's their National Measurements Laboratory. So we use a NIST-approved system, which was developed by Agilent. In those days, we were HP, but it was developed by HP in the early days and accepted by NIST. And it uses a ratio method. So we have a reference power sensor, we have a ratio power sensor, and a validation power sensor. Now, a validation power sensor is the same precision as a reference power sensor. So once we calibrate our system, the first thing we do is put our validation sensor on this. So every time we do...
Every time a new bit of kit comes in?
Every time we do a new sensor for a customer, we're doing a validation on our reference sensor against our validation sensor.
Got it.
For not just the power, but also for the VSWR of the sensor. VSWR is a significant component on it. If you use the simple method, you're not actually taking into account the uncertainty associated with the VSWR of your device under test.
Which seems crazy. Why would you do that?
Why would
because
you do
it's
it?
cheap and easy?
It's cheap and easy. All right. So we've got, internally it's probably about nearly about $400,000 worth of equipment devoted to calibrating our customers' power sensors.
Right.
We are expensive, by comparison we are expensive to our competitors for calibrating power sensors. Not all of our competitors use a similar method to this.
But if you're serious...
If you're serious, that's right. So you've got to have a low frequency source. You've got to have a 2-channel power meter. You've got to have a low noise, high frequency source. Some associated amplifiers. You've got to have reference power splitters. Now, a power splitter is a power splitter, right? It's two resistors,
exactly.
and a common
it's
point.
Easy, right?
How hard is it?
Tell us.
We need to know the effective source match of that reference. So to do that, we have to combine 9 parameters associated.
9 parameters just for a
So we do the S11, S22, S33 parameters, and all the parameters associated with that intermingling in a vector quantity to come up with the effective source match of that power splitter. That's before you start.
Before you
actually
even start
working,
to
you actually got to do the science in the background. All right. So as part of that, we use the VNA systems, our VNA and ENA systems.
And you do that each time a new customer's.
No. That's only once. That's on its cal period. So we've done that. We had that data. That data's in the system, and as we spoke earlier, that calibration is only valid 2 points in time.
Yep.
So if we get to this point in time and it's faulty, we're in trouble. We have to look back. We have to look back in time and find out everything that we've tested using that faulty bit of kit, and what the impact is. In terms of our customer, that means on very rare occasions we will recall the equipment that we've calibrated and say we've had a faux pas. All right, something's gone duff on us. We're confident that the measurement we gave you is good, but we need to recall your unit and recalibrate it without charge, because it's our responsibility. It's part of our quality system that if we find a fault with a piece of equipment, we will recall it. So that's those 2 points in time. It's in our best interest to look after that gear, because it's a lot of work involved in doing that, just doing the analysis side of it. So it's in our best interest to look after our gear properly. So we do that. Our precision cal kits that we use, the example I gave earlier is we've got a precision cal kit in our mobile facility that's been in use since 2000. And it's had one failure in that time, and that was a catastrophic failure of a connector. So that's not a wear and tear thing, and it boils down to the way you look after your equipment.
We were talking about connector science before, connector care before.
Connector care.
Tell us about why it's so important to take care of your connectors.
All right, if you're looking at it, you pay a lot of money for these devices. I don't know if you can focus in there. Can you see that? That's a metrology grade connector.
That's
metrology grade N-type connector. Now, most of the N-type connectors out there are production grade or less. Often you'll see an N-type connector and it's got a point on it. It's got a sharp point on the end of it, It's like a taper. All right. If you're working with precision equipment and you buy a $20 connector saver that's got that tapered pointy bit on it, you're actually going to cost yourself a lot of money, because you put that less precision connector onto your metrology grade connector, you're going to blow it away. One of our customers had turned around to us at one stage, because we visited them every year and did all their equipment, including their cal kits. They were spending between 10 and 15 grand a year on repairs of their cal kits.
Just repairing
connectors that we'd picked up as part of the calibration. They turned around to us and said, these products are unreliable, and a bit of a red flag to a bull, and we said, it's not the product, and we used the example of ours. So we sat down with them, walked through the problem, walked through their connector savers that they were using, walked through with their operators, gave them training on site, taught them about connector care. And if you imagine, particularly with precision equipment, a male and female connectors, I'm not being sexist when I say this, so this is what they're called, male and female connector, the biggest source of damage to a male and female connector is moving the whole body. Because when you've got a male and female together and you move it like that, you can feel the friction in your finger. That's exactly what happens within the connector. So your connector return loss, instead of being the order of 49 dB, suddenly becomes 40 dB, 30 dB, in some cases 20 dB.
Because the return loss is directly related to the physical dimensions of
That's
the connector,
right.
And you're scraping off.
You're causing wear and tear on it.
Physically causing wear and tear.
Which changes the dimensions of the connector, which particularly at higher frequencies. Now, Dave, you're a low frequency guy, but it's not so much at low frequencies. But say below 45 meg, it's not that big a problem. Above 45 meg, when you start to get in the gigahertz region, you start to see these things, they start to impact above 2 gig.
Right.
And you'll see it's almost a straight line.
Yep.
After that, when the people have misused their connectors.
Wow. Okay.
The impact of that with a network analyzer like this one here, you might pay, this is an ENA, or it's a low frequency network analyzer, you might pay 30 grand for that product to get it, and it's a key part of your business.
Yep.
The performance of this as a product is directly related to what you're putting out to your customers. Now that one worn connector on your cal kit, suddenly instead of having a return loss of 49 dB on that load, if you've got a return loss of 20 dB,
oh, you're
all right, your load's not real good. And if you're using a load that's not real good as a reference, your network analyzer thinks, because that's the way it's built, that return loss default characteristic for this device is built into it. So it's looking for something that's better than 49 dB. If it's got something that's 20 dB hooked up to it, suddenly the performance of your device under test is significantly better than what it really is.
Aha, so you're led into a false sense of assurance, you send out a product you think's good.
Your confidence levels actually disappeared.
Yes.
All right, your confidence level in the product that you're selling has actually gone out the window. And if you don't have a quality system in place that can track what product you've used that one bad connector on, you may be in a situation where you have to recall a lot of product.
That's it.
And the recalling product is something companies don't like doing.
No, it's nasty.
We don't like doing it. We have done it on occasion, but it's part of our quality system. All right, so
can you show us the difference between a metrology grade connector and a regular connector? Oh, we've got some goodies over here in the drawer. What's in the drawers? Lots of fancy connectors.
This is another N-type connector. This is a field grade connector, and It looks like a precision piece of kit. It's not your
It does. It looks like a decent quality one. I would say I could scratch and sniff that. It looks pretty good.
Yeah, it's probably good for general use up to about 8 gigahertz.
Right.
All right. An N-type precision N-type connector is generally rated to 18 gigahertz.
Right.
All right. So you need that different collet and sleeve that's in there. And the precision of that device there compared to that device there determines the return loss of the connector.
Got it.
Each time you have a connection in your system with a poor return loss, you're losing something.
Yep.
You're losing information or quality within your RF system.
Of course.
So,
and the difference is
it's the precision of the dimensions inside. Generally, you'll have instead of just having a knurled nut on it, you'll have a nut there that is made to fit a torque wrench.
A torque wrench. So you don't actually screw the entire connector on.
No.
You simply you push it in and then rotate it.
Going back to the problem our customer had with his operators and everything else, the easiest way to put an N-type connector on is to grab the body of the device and just spin it. Yeah. All right. Which is exactly what you're doing with that.
And you're wearing the connector.
If you grip one finger in your hand and turn it, you feel that friction. Yeah. That's exactly what happens to the connector. So
and you're changing the return loss directly by each time you do that.
Each time you introduce wear and tear, so we use a couple of spanners to alleviate that with the precision devices, and we just torque wrench them up. All right, it's each type of connector has a different torque wrench. The types of connector that we generally use 7mm, which is an APC 7mm connector, which is a sexless connector that goes to 18 gig. Very good, very, very precise connector, not in general use. Right. It's probably more standards laboratories than anybody else. The most common connector you will come across in this industry is the N-type connector, which is the Navy connector. B&C and TNC, not generally used for precision devices. They are used low frequency devices. They can be good to, the connector itself can be good to about 500 meg before you start to see any real damage. We generally don't use them in that frequency range in here. But the other devices that we use 3.5mm connectors and 2.4mm connectors. This is related to the cross-sectional area of the contacts. Got it. All right, so it's not 7mm wide. No. All right, it's the area of it 7mm wide. The N-type Navy connector was developed in the 40s. The APC 7 or 7mm connector was also developed 50s, I think. I'm spitballing it here. Yeah, well, I'm only a young fellow myself. And the 3.5mm developed from other connectors. All right, so the frequency limitations of each range. Generally speaking, an N-type connector is good to 18 gig. In some cases, it's good to 22 gig. Right. The 3.5mm is good to 26.5 gig. Can be good to 33 gig. And then we start to get into the K-band connectors, which are compatible with 3.5mm. Then you get to the 2.4. 2.4mm connectors are good to 50 gigahertz, which is the top end of our frequency range here. We can go higher. We can go to 1mm connectors, but we have to get some younger metrologists in for that, because you're talking about a very fine connector, and some of my vintage is a bit challenging with those connectors. So we get to supervise the people with good eyesight when it comes to that. All right,
so this kit here is basically for just calibrating RF power sensors.
That's the main part of it. Yep. But we also do S parameters for filters. Yep. Couplers.
Would you do cables and stuff like that?
Yeah, cables. We can do cables. We do TDR measurements on cables. Customers have delay lines, and they need us to. So they need us to how often does a delay line change when it's in a box and it's got two connectors on it? But we have to calibrate it for the customers, because that's a quality system. We do couplers. We do attenuators, filters. These are all S parameters. So the 4 S parameters that we work with are S11. S22, S12 and S21, which are the 4 directions in that two-dimensional network. Right. We haven't gone into X parameters in Australia. We haven't had a need to. We can provide the calibration and traceability for X parameters, but our devices don't need X parameter testing. So we are purely accredited for S parameters in that range.
Excellent.
All right.
And that's $400,000 worth of kit just to calibrate.
That's right. That's right. And there's a bit of science behind it as well.
It's all science. Calibration is... That's what sets a standards lab apart from a regular calibration lab, right? There's a bit more science behind it?
Well, no, the science is the same. It's the precision. It's precision that's different.
Precision.
All right. So any quality system, any calibration that you do is a measurement against a reference.
Yes.
All right. If I give you a steel rule and say it's been measured to a traceable standard, that's fine. If I measure it against another steel rule and say this is good for 30 centimetres plus or minus 5 millimetres, all right, that's fine. The difference is if I send it off to a standards laboratory, it'll be 30.005 centimetres, just plucking a number out of nowhere, plus or minus so many microns against the laser interferometer. So it's the difference in precision.
Got it.
More than the method. The methods, there always has to be a repeatable method. There always has to be a documented method. There always has to be a quality system that backs it up. There's no point in a box coming in and me deciding I know how to do it and just plugging it in, calibrating it and saying, yeah, here's your box. All right. It's really, you've got to have that documentation behind it because that's the basis of your quality system. Part of your quality system is you have to keep a record of what you do. You have to keep a record of the calibration report and the certificate. We do that in a PDF format and it's globally backed up. So currently we've got about 7 years worth of all the customer work that we've done in the last 7 years and your internal work on a global server that's maintained and backed up and is accessible by customers as fast as they can get in the web. Now that brings you to the question, if someone turns around to you and charges you an extra $150 or $200 to provide a report, are you paying for a copy of their PDF report, or are you paying for something else? All right. So our standard offer as a calibration is to provide not only the quality system and the calibration, but we provide the report and the certificate as either a hard copy, the soft copy, or both.
Got it.
All right. So the soft copy is available to customers that go onto our system called InfoLine. So if you've got a customer with a huge database and a calibration lab or a production laboratory has to maintain its records. So years and years of records get bigger and bigger and bigger and harder to store. It's acceptable to store things by PDF.
Right.
It's acceptable to have a third party store them. So some of our customers are now using us for the storage of their records.
Oh, okay.
Because we have to store them anyway.
That's right.
And they can
access. Why do it themselves? Yeah.
Why do it themselves? They can through InfoLine they can access that information as fast as they can type their login into it, and pull up the full history of that device.
Got it.
We're supposed to maintain it for at least 7 years within our quality system. We're getting stuff maintained at least 10 years in some instances. When we started doing it. When we started doing the on-site work, we'd do 200 jobs. We would come back with this much paper because that's how much paperwork we gave our customer, right? Now, when we finish the job off, within an hour of the last job being done, we present all the data to the customer on a CD, and he's got a smile on his face. Instead of going through each piece of paper, he's able to pull it up and check it up. If his quality system needs him to order it, he can pull it up on the web and do it that way.
Beautiful. And this bit of kit is more than just buying off-the-shelf top-end bits of Agilent gear and sticking it in a rack and thinking you know what you're doing.
Background behind it as well. We have to maintain it, and we have to maintain our traceability, and we have to maintain our confidence level.
It's not powered up, but there, folks, is a 3 hertz to
50 gigahertz.
50 gigahertz
measuring receiver.
Measuring receiver, which does basically
everything.
It does from audio stuff. It can do audio analysis too.
It goes from, as I said, from 3 hertz to 50 gigahertz. As a measuring receiver, it's good from 5 meg up to 50 gigahertz on 1 hertz bandwidth. As a measuring receiver, you can do modulation characteristics including it includes an audio distortion analyzer built into it. It can be optioned up for other things. It can be optioned up as a noise figure meter. It can be optioned up as a phase noise system. Not as good as the E5500 series, but it can do phase noise close, relatively close in for those noisier sources.
Got it.
So, like the EEG oscillators and the like.
What have we got in the cabinet there?
Oh, that's just a storage.
Yeah, come on. People love seeing like real sexy connectors in drawers and stuff like that. They do.
All right, we just keep some of our standards here. These
Calibration
are 7 mil. We talked about different connectors yesterday. This is 7 mil sliding load cal kit, mechanical cal kit. The 7 mil connector is probably one of the best connectors. For those of you that haven't seen it before, it's what we call a sexless connector.
Yep.
And that's an open circuit. You think, why on earth would you have an open circuit? It's a relative. So it's a relative device for our short. So we've got a short and open there.
Got it.
All right, that's a short and open. That's so. These devices, as we spoke yesterday, they are go back to dimensional
tolerances and yep. So they go back to basic dimensional standards.
Yep, and the type of material that's used. So that's the opens and shorts. But if you look at that's a broadband load, and you can see that the connector in the centre, the contact in the centre, is sexless. So it's not a male or a female.
Yep.
All right, it has a sleeve around the outside of it. So you get those two planes mate together.
Right.
Through that sleeve, and when you do them up, instead of having a male and female, all right, you have two like devices there, and you hook up. You only turn one of them.
Yep.
All right. Commonly, when we see devices come in, they've got the 7 mil connectors on them. People grab a set of Stilsons and tighten both of them up.
Is that right?
It's probably not the best thing to do for them. We talk about connected care, but what that does is put the connector under too much pressure.
Yep.
And can damage the front end of your unit.
Got it.
Cool bananas.